Hi and welcome to this third video about the preparation of nitriles by alkylation of cyanide. This presentation is about the alkylation of cyanide with alkenes. Most reported examples are Michael additions of cyanide to electron-deficient alkenes, but I'll also show you some examples of the cyanation of simple alkenes and alkynes. This is a typical example of such a Michael addition. The rate of these reactions is strongly influenced by the number of substituents and steric crowding at the alkene. Here, only the less substituted olefin reacted, and a mixture of diastereomeric nitriles was obtained in high yield. No addition to the carbonyl group occurred because cyanohydrine formation usually requires acidic reaction conditions. In this example, cyanide added to the condensation product of benzaldehyde and diethylmalonate. Because malonates are easier to saponify by intermediate ketene formation than simple esters, saponification and decarboxylation of only one of the two ethoxycarbonyl groups occurred. Here, a similar reaction was conducted in the absence of water and under less alkaline conditions, and no saponification occurred. Interestingly, cyanide added to the di-substituted crowded alkene in high yield. Cyanide can also be added to isophorone, the cyclocondensation product of acetone. Here, less than one equivalent of neat hydrogen cyanide was used, and the addition was catalyzed by a mixture of lithium hydroxide and toluene sulfonic acid. In this example, an epotylone analog containing two alkenes, an epoxide and a lactone, was treated with a large excess of potassium cyanide and DMF. The main reaction was Michael addition to the electron-deficient alkene. It has been reported that with the aid of enantiomerically pure Lewis acids, enantioselective cyanide additions to alkenes can be achieved. Here, a chiral gadolinium complex brought about 96% enantiomeric excess, what is impressive given the small size of cyanide. Enantiomerically pure phase transfer catalysts can also mediate such enantioselective Michael additions. In this example, an enantiomeric excess of 90% was attained. Nitroalkenes, readily available by condensing nitromethane with aldehydes or ketones, are also good Michael acceptors. With only one equivalent of cyanide, the expected nitronitriles will usually be obtained, but with an excess of cyanide and under strongly basic conditions, elimination of nitrite can occur, as in this example. Styrene is a weak Michael acceptor only and does not usually react with cyanide. In the presence of nickel-0 complexes, though, styrene and related alkenes can undergo hydrocyanation. Here, a phosphide was used as ligand, and 5% of nickel was enough to achieve a complete conversion in 16 hours at 60 degrees Celsius. Alkenes that readily form carbocations with acids can sometimes yield nitriles upon treatment with hydrogen cyanide or trimethylsilyl cyanide. Here, such a hydrocyanation was performed with an excess of trimethylsilyl cyanide and triflic acid. The initially obtained mixture of diastereomers was epimerized in high yield to the target isomer by treatment with an alkoxide. Careful optimization of such hydrocyanations will usually be required, and typical side reactions include oligomerization of the alkene, Frill-Crafts alkylations of arenes, and the formation of isonitriles. Like styrenes, also simple non-activated alkenes can undergo hydrocyanation under nickel catalysis. Mixtures of regioisomers may result, though, as in this example. An alternative to direct additions of hydrogen cyanide to alkenes is the cobalt-catalyzed cyanation shown here. This reaction proceeds by intermediate formation of an alkyl-cobalt intermediate, which fragments homolytically into an alkyl radical. Cyanation of this radical with tosyl cyanide proceeds in high yield and under mild conditions. This reaction is well suited for the cyanation of polyfunctional alkenes, as in this example. I have described the precise mechanism of this reaction in my video about the hydrogenation of alkenes with silanes. 1,3-dienes are similarly reactive as styrenes and do also react with hydrogen cyanide in the presence of nickel catalysts. This here is an example of the hydrocyanation of cyclohexadiene, which gave a good yield of cyanocyclohexene. Examples have also been reported of the addition of hydrogen cyanide to alkynes. Interestingly, these reactions can be performed in such a way that no second cyanide addition occurs to the newly formed acrylonitrile. As shown here, though, mixtures of regioisomers may result. Let's check some potential side reactions. Also during alkene hydrocyanations, isonitriles can become an important byproduct, in particular under acidic conditions. In this example, a low yield of terz-butyl isonitrile resulted upon treatment of isobutene with hydrogen cyanide and cuprose bromide. The initially formed copper complex was demethylated with aqueous potassium cyanide. Acidic reaction conditions may also yield formamides from alkenes and hydrogen cyanide, the Ritter reaction. Here, the Diels-Alder product of isoprene and acrylonitrile yielded formamides when treated with an excess of hydrogen cyanide and sulfuric acid. Careful optimization was probably required to prevent hydrolysis of the product. Cyanohydrines are formed when aldehydes or ketones are treated with cyanide and acids. It can be difficult to predict if cyanohydrine formation or addition to an alkene will be faster for a given electrophile. In this example, exclusive cyanohydrine formation occurred, despite the excellent steric accessibility of the alkene. Nitriles with strongly electron-withdrawing groups readily undergo hydrolysis. Here, an alpha-fluorinated nitrile was formed by Michael addition of cyanide to a fluorinated alkene, but instead of the nitrile, only a mixture of sodium carboxylate and amide could be isolated. Nickel phosphide complexes can also isomerize alkenes in unexpected ways, as in this example. Interestingly, no enamines or cyanohydrines were formed, and mostly the hydrocyanation product of the terminal alkene was obtained in high yield. Here are some further references which you can also find in the description of this video. The next and last video of this playlist is about the alkylation of cyanide with aldehydes or ketones, that is, the preparation of cyanohydrines. These products are important intermediates for the preparation of alpha-hydroxy or alpha-amino acids. See you then.